about the exam. Okay, so I understand that. I understand that most of you have this major concern about the examination. So I will actually talk about this, and am able to record it. So students who are not arriving here, at least they can know it later. Is that in this programming, in this course, the examination paper would not contain any questions that require you to write any programming. There will be no programming questions in this examination. There will be 0 programming questions in this examination. All we are asking in the examination is testing your ability to understand the algorithms. Okay, this is one major thing that I hope everyone can understand. Okay, because I understand that many students have a strong fever or strong fear, okay, about they are getting very afraid about programming, about having programming assignments during the examination. So I will make a announcement first, announcement here, okay. The thing is still not finalized, okay. I will do a formal announcement in the next week, okay, but you can expect that there will be no programming questions in the examinations, okay, if everything goes well. And about the group project, okay. In the group project, the group project specification and a tutorial on the group project will be released very soon. Okay, I will release it tonight. Okay, the reason why I cannot release it today, or yesterday, is because I'm busy working on the finalization of the examination paper. And for the group registration, okay, you can go to this page, and then you can add your group here. You can create your group, and then your or another group member need to join that group. Okay, and then you can finish the group registration. Okay, you said that, okay, Professor, doing this registration is so complicated. I don't know how to do it. Don't worry. Just look at the instruction. Okay, I created a set of notes to teach you how to create a group in the Moodle and how to do the finish the registration by asking your group member to join that group. Okay, please remember one thing is that when no matter you are doing the project on your own, or you are trying to do the project as a team, please set up the password. Please set up the password. Okay, and the reason of setting up the password is to avoid any strangers just randomly entering your group by accident. Okay. Okay. So for latecoming students, okay, for students that just arrived, okay, we are talking about 2 things. We are talking about the examination. The examination will not contain any programming questions, okay, and it is not fully finalized. But if everything goes well, that will be it, okay. In the examination, there will be no programming questions, okay. And for the group project, okay, the group project specification and the tutorial related to the group project will be released to the Moodle very soon. And the group project registration is not available. You can register your group, and the detailed instruction of registering the group is available on the Moodle. Okay. Okay. Please follow the Moodle instruction to register your group. Okay. And the deadline is next week Wednesday. Okay. Next week Wednesday. Okay, so any questions about the group registration? Okay, the registration system is a bit complicated, so I created a set of notes to explain how it can be done. Okay, essentially, if you are 2-person group, then you need to assign 1 person to be group leader, and the group leader need to create a group in the Moodle's group registration page, and the group leader will also set up a password for that group. Okay. And after the group leader finish setting up the group in the registration page, then the group leader will send the password to his or her group members. And the group member will add himself or herself to his or her group. Okay? But if you are trying to do this project on your own without any partners, then you can skip the second step. Okay? Simple as that. Okay? So any questions? Any questions? So remember to form your group before next week Wednesday. Next week Wednesday. Any questions? Any questions? Any questions? And I'll upload the lecture 5 to the Moodle as well. These days I'm really busy finalizing the examination paper and working on other things. So I haven't been able to upload the lecture notes 5 to the Moodle system. Okay. So any questions? So any questions? Any questions? I will do a proper announcement about the examination next week. Okay, but if you take a look on the registry page, you will note that all the examination time has been finalized. Okay, I don't know if you know that. Okay, in fact, all the examination in the second of the classes in the second semester, the examination time and venue have been finalized. And I believe that you can check it out in the registry webpage as well. Okay. Okay. So please remember to mark down in your calendar and remember to take the exam punctually in the expected venue. Okay. So any questions? Any questions? Any questions? If no, then let's go on. Wait. Okay. So last time we actually start talking about lecture 5. We actually start talking about lecture 5 about solving about chess, okay, about chess playing, okay. So these are actually different kinds of chess, okay. For example, the checkers, the Go chess, the backgammon, and also the Othello, okay. So all these games are involving different more than one players, and they are competing with each other by manipulating the chess pieces in the chessboard. Okay, and when we are working on games, the most important factor that is different from your ordinary search problem is that you now have two agents. Okay, you now have two agents. Okay, so your action, the action you would have done will not have a decisive effect on the environment. In the search problem, when the agent do an action, the action will change the environment in a deterministic style. Okay, this is how single state problem is supposed to be. But in the game, not just you are manipulating the chess pieces, your opponent is also manipulating the chess pieces. So for you to find a sequence of action that allow you to win is not just thinking about yourself, you will need to think about your opponent as well. Okay, so in your search, you would need to not consider your action, but also consider the action of your opponent as well. Okay, and although I believe that not anyone here have experience of playing chess, including me. Okay, to be honest, I don't play chess. I don't play chess. Okay, I don't play chess. I don't play Go chess. Okay, but I believe that you should have watched some online stream about chess. Okay, so for example, I believe that most of you have because in the past, okay, like 5 to 10 years ago, when AlphaGo is very popular, I believe that most of you at that time will take a look on the live stream of AlphaGo against state of the art Go chess player. Okay, So in that game, you will actually find that the end game is not the only property that we need to consider when the game ends. Okay, so in the single state problem, when we reach the goal state, then we stop everything, right? Okay, we don't care about how we get to the goal state. As long as we can get to a goal state or a state that satisfies all the properties of a goal state, then we'll stop. We don't care. We don't care about how good or how bad our goal state is. In fact, we don't have a mechanism to measure how good or how bad the goal state is. Okay, as long as that state resembles the properties of a goal state, and if we are able to find a sequence of action that reach to that state, then we call it endgame. Then we call it okay, end of story. But chess game is another story. A chess game is another story. If we want to make the computer playing games, we don't just want the computer AI to get to the end of the chess game only. We want the AI to win. Okay? It is totally making nonsense if we make an AI who just lose all the time. Okay? Technically speaking, an AI losing the game or the AI winning the game or AI having a draw with the opponent, these actions all can lead to the end of the game. Okay? So if we are using the single state search problem logic, then our AI will just lose. Losing doesn't mean anything. Because in a single state problem, as long as I can reach the end, then it's okay. Okay? A chess game, whether the AI win or the AI lose or AI draw, they all be considered as the game end when the game really ends, right? So using single state agent logic, you cannot write a AI that play chess. Okay? Because single state problem agent, what they are good at is, okay, I find a sequence of action that get to the goal state. Whether the goal state is good or not, I don't care. I don't have a measurement to measure whether a goal state is good or whether a goal state is bad. But when you are playing chess game, that is something you should consider. You should get to a end point of the game that you can win. Okay? Then the next question you will want to ask is, okay, so Professor, I just add a free state, a fact, okay? 1 means win, -1 means lose, and 0 means draw, okay? Is that all right? It depends on the game you are working on. For example, if you are working with the game of Go, that is 圍棋, okay? 圍棋, okay? If you ever watch the live stream of AlphaGo versus Go Chess Master Player, you will find that when they end the game, they will need to do counting to count how many points you gain and how many points the AI gain, and the player that gains the highest point can win the game. Because I'm not a person who is good at who know how to play Go chess, so I'm talking about it using my limited understanding on Go. Okay, in Chinese that will be something like 圍棋要數目㗎嘛。So I guess you know what I'm saying is that when you are playing with 圍棋, when you're playing with Go chess, when you're playing with 圍棋, okay, at the end you just see, okay, some chess pieces get killed, so this game end, okay. In chess, okay, we have the so-called checkmate, right? That if the king is in danger, okay, then the game ends. Okay, So there is the determining factor of the chess is very simple. But if we are working with Go chess, then we would need to count the points gained by both players and compare both points, and the player that gets the higher point wins the game. So in the Go chess, you can have a win that win the opponent in a major victory, or you can win your opponent in a slight victory, depending on how many points you are leading him or her.
Utility points.
Yeah, so you should need utility points. Okay, so we need to use a value, a utility points to represent the end point of the game. So this is one major differences between single state problem and a chess playing AI. We need to introduce utility value to measure how good or how bad the end game is for the AI agent. Okay, and you also need to consider one more thing is that when you are playing the chess, you don't just consider your actions, you also consider the action of your opponent. Okay, the game is dynamic. You are not the only player who is playing the game. Okay, okay, just consider this. Okay, I will use my favorite example once again. So in Avengers 3, okay, when Doctor Strange, okay, need to explore the parallel universe to find a way to defeat Thanos. He will not just watch how Avengers move, how Avengers action. He will also watch how Thanos action as well. Right? You cannot find the way to achieve victory by just looking at yourself. You need to also consider your opponent. Okay. So when you are playing, you must be also guessing whether your opponent is having draw 4 cards. Okay? Okay? Or you will try if I have one draw 4 card, I will need to guess are other opponent having draw 4 card. If I place this draw 4 card here, will other players also place that draw 4 card, and at the end I need to draw 12 cards, okay? Or 16 cards. Okay? This is when you are working with AI that play chess, you don't just think about your own action. You need to think about your opponent's action as well. The simplest example is that when you are playing, when you have the draw 4 card, you will need to think about, okay, whether my opponent have 3 draw 4 cards at A10.
Yes.
Okay, so that you can avoid the draw 4 getting back to you. Okay, so the most painful thing is that you have one draw 4 card and you are playing with 3 other people, and 3 other people also have one draw 4 card. You place one draw 4 card, the other people also play one draw 4 card, and suddenly you need to draw 16 cards. Okay, so when you are playing games, you don't just think about your own action. You need to think about your opponent's action. Okay, so this is the 2 major differences that is different from single state search problem versus playing games. Okay, and you all know that AlphaGo is very good. Is able to beat the state-of-the-art human player. So I will skip it. Okay, you can read at home. Okay, so let's dissect what is the similarity between the game and the search problem. So in the game, you still have search state. You still have the state of the game. Okay. So for example, if you suddenly need to leave if you are playing chess with others, if you suddenly need to leave and take some refreshment, okay, you will need to keep a record of what is the chess pieces position right now in the chessboard. Okay. Okay. So the positioning of the chessboard, you can consider it as the state of the game. Okay. So game has state. Okay. when you move a chess pieces, then you are moving the game to the next stage. Okay. Okay. So if you don't able to understand this concept, you just recall this in your mind. Okay? So I believe that most of you here have been playing all sorts of board games with your classmates or schoolmates or secondary schoolmate or whatever during the gathering. Okay. I don't know your generation, but at my generation, when people do gathering, will play board game. Okay. Okay. Maybe for example, when you are playing board games, when someone need to leave the board, leave the game for a while, then you may want to stop the game for a while. And when you stop the game, you want to keep the positioning of the chess pieces unchanged. Okay. The reason why is that the moment the positioning of the chess pieces is being moved, then the game is being disrupted. Okay, the positioning of the chess pieces, they are actually the current configuration of the game, and they are actually the state of the game. Okay, and the second is the action of the game. Okay. So when you are playing a chess game, you must do action following the game rules. You cannot make something up. Okay. So for example, the queen can move horizontally, vertically, and diagonally. Okay. And the soldier can only move, or the pawn, okay, I don't know the exact word. Okay. They can move one step forward only. Okay. Okay. Or in Uno, okay? Or when you're playing Uno, if you have only 2 cards left, you will need to do the action of calling Uno, okay? Before you pass your turn to the next player. Okay? All these are action rules, all these are game rules. The game rules will actually limit the actions that is available in the game. Okay? Okay, you cannot take action that is illegal, and as a result, you will get disqualified for the game. Okay, so one more thing that is similar to the single state problem is that we can actually define the state transition function as well, because we know the game rule. The rule book after programming can be converted into the action of the game. The action or the state transition function of the game. Okay. And game playing is that you are essentially playing against the simplest case is that you have 2 players and you are playing against each other, and both of you, the goal is to minimize the chances that the opponent can win. Okay, or in other words, you will want to make sure your opponent get the worst utility score for your opponent. Okay, or in other words, I can say you are trying to get the best utility value for yourself. Okay. Okay. And why we want to discuss game so much in AI is because game is hard to solve. When we are talking about chess, okay, we have 50 moves, so we have around 50 states by each player. Okay, so 50 moves means 50 states. Okay, so the third state is around 35 powered by 100. Okay, because 50 moves per player, that means that we have 100 turns. Okay, 100 turns, that is 100 states, and we have a benching factor of 35. So 35 powered by 100 equal to 35 powered by 100. Okay, so I don't want to put this in the calculator, but you know how big this number is. Okay, you know how big this number is. Okay, go. Okay, I don't know if you have ever think about this question. Why Google spends so much money, so much effort to develop AlphaGo? Why Go? Why not other chess game? Because Go is the most difficult chess game that you can have. That is deterministic and fully observable. Okay, and the branching factor is around 250. Okay, and it will have around 211 moves. So the search tree have around 250 powered up by 211 nodes. Okay, okay. So imagine your AI need to go through all these possible route, 250 powered by 211 possible end game scenario to find the winning solution. This is almost impossible to do. Even you have superpower, okay? If you recall in the Avengers movie, the number is far less than this one, okay? Okay, even you use AI, you just cannot compute this. Okay, so how Google does this? Simple heuristics. For example, I can take a look on 10 moves, then in a particular node, I use heuristics. I know that the possible values, the possible utility values under this route would not bigger than a particular value, okay? And that is the AI will lose in that route. So the AI will just drop that route altogether. Okay? And if you take a look on the PowerPoint here, AlphaGo use two techniques, CNN and Monte Carlo, okay? So in the future, you will need to study a course related to simulation. And you go back to, and in that course, they will teach you what is Monte Carlo, okay? Okay, essentially Monte Carlo is a good technique to simulate the outcome of something through trial and error. Okay, through trial and error, okay? But of course, it's done in a efficient technique that using it on AlphaGo makes sense, okay? Okay, for the detail of CNN and Monte Carlo, I will not discuss this in this course. You will learn it in the later advanced courses on machine learning and simulation. Okay, we have one course on dedicated of machine learning that will talk about CNN, and we have one course dedicated to simulation, and it will talk about Monte Carlo. Okay, so I will not go into technical details on these things. Okay, and games are more like the real world than standard search problem. Okay, because in the real world you will not just interact with one play. You will not just work on a problem with one agent. You will need to compete with other agents. So that is why we say that the game is more like the real world in this regard. And games actually penalize inefficiency very severely. Okay. One major example here is if I am playing a game I'm not talking about chess game, okay? I'm talking about ordinary computer games. If I am playing games such as Age of Empires or Red Alert 2, and if the AI agent need to think about 1 minute when it make a move, then I will be extremely annoyed. Okay? Okay. So if you are playing other kinds of games, for example, if you are playing FPS, okay, first person shooter, okay, if your opponent is moving very slowly, and each time you need to take about minute to think about next move, your opponent need to think about the next move for 1 minute before it can take another shot on the other person, then you'll find that that FPS game is not fun as well. Okay, so not just chess game, almost all the game in the real world actually penalize inefficiency very much. Okay.
Because if you think too much, it's already the yesterday's news.
So here is a Chinese saying that I keep hearing. but it is maybe a little bit it is a little bit I'm not saying that it's totally correct, but you can sense where is logic come from. 打機並不令人暴力，叻機才是。Okay? Okay? So, why video games doesn't make you violence? The game stuttering and the game need to load for a long time will really make you violence, okay? So this is other things saying that when you are creating a game, when you're creating a game AI, inefficiency is penalized very severely, as if your players would do. So what about chess game? When you are playing in an international competition, chess, no matter it's chess or Go chess or whatever chess, it will have a timer that force you to that restrict the amount of time that you can think about your move. Okay? Okay. If you are not able to make a move in a specified time period, then the game will make a random move for you. Okay, this rule exists for chess and also Go chess as well. If you take a look on I don't know if you ever watched the live stream of chess game. Maybe you have watched it during the time that AlphaGo is very popular. You will find that when a chess player make a move, he will need to press the button on the clock to signify, okay, I finished my move and the time is ... okay? Okay, there is a timer next to the chessboard that count that run do a downward count on the remaining time each player has to think about his or her move. Okay, so if your AI is not able to finish its decision making within that time frame, then it will lose the game as well. Okay, so computer game in general, players don't enjoy AI that is slow, that is laggy, and if you are really playing chess games, you have a time limitation that you cannot exceed. Okay, so it penalizes inefficiency very severely. Okay, okay, and if a chess game is 10% less efficient, then it will be far weaker than you expected. Okay, so we actually have two different methods to handle this issue. The first one is called pruning. Okay, we just skip a proportion of the tree that will not give us good solution. And the second one is heuristic function. We instead of exploring the whole search tree, I stop at particular depth. Then once I reach the particular depth, I just use the heuristic function to calculate my utility value and I use it as the terminal state. Okay? Okay. For heuristic function, I've already mentioned how it works in the previous lecture, so I will not repeat myself. And the second issue here is that different chess games have different heuristics. It is strongly tied to the nature of your chess game. Okay? Okay? Okay. Just like if even though it is substantially similar, okay? They are both first person, okay? But first person shooter game and first person shooter flight simulator is two different kinds of games. You cannot use the heuristics, you cannot use the instinct you develop playing first person shooter to play first person flight simulator. It doesn't work. Okay, so different games have different heuristics. Okay, chess game and Go chess have different game rules, so of course the heuristics is different. Okay, But so we will not go into technical details on talking about heuristics. In this lecture, we focus on pruning. Okay. And here we do a classification of the game. So chess, checkers, Go, and Oteo. You can see all the chess pieces in the chessboard. And when you make a move, the chess pieces doesn't move around. So it is deterministic and you have perfect information. That is fully observable, okay? Monopoly and backgammon, okay? They are perfect information, but you are by chance. Okay? When you are playing Monopoly, you need to roll the dice, right?
So fast.
Okay. So the rolling dice actually adds the stochastic nature to your Monopoly. Monopoly in Cantonese is called 大富翁, okay? 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 I don't know if you play around Monopoly in the past. Okay? But Monopoly is a game by random. It's game that has randomness in it. The reason is you need to roll the dice each time to determine how much move you can move. Okay? Okay? Or if you step upon the place, the tile that allow you to draw some cards, okay? Okay, draw some chances card, okay? Then that is by chance as well. Okay, so Monopoly, you have perfect information because you can see all the chess pieces, all the housing estate in the whole game. Okay, but it is by chance, because you simply don't know how much step you are going to take when you roll the dice. Okay. Okay. So any questions? I guess all of you at least know what is Monopoly, right? Okay. So I will not explain it further, okay? Back in my days, okay, to be honest, personally speaking, I never played the proper version of the real version of the Monopoly. I played the $1 version of the Monopoly on the computer. Maybe that is too old for your generation, okay? Okay. And the next, and we have the kind of game that is imperfect information and by chance, okay? For example, bridge, poker, scramble, and nuclear war, okay? So for poker and bridge, okay, you don't know what card your opponent is having, and each time when you take a card, it is by random. So you don't have perfect information, and you are doing all the things by chance. Okay? Okay?
Nuclear war doesn't refer to the real nuclear war, or is there?
The game.
Oh.
The game. The board game. So any questions? All the things that talk here are the real board games, okay? Not anything else, okay? So any questions? One thing I would like to talk about as well, okay? In case you are taking other courses. So although in this lecture notes, we are talking about algorithm for games. We are not talking about game theory, okay? Totally different thing, okay? Okay. Just to make sure everyone get this idea, okay? Because I don't know if you are going to take a course of game theory in other department, okay? Because I believe that in economics, we have economics department and we have business department. They probably will all offer a courses of game theory. But this lecture notes is not talking about game theory. It's not talking about game theory, okay? It's talking about computer algorithm, okay? So now let's talk about the most simplest case. Okay, in fact, in this lecture notes, we will only talk about the simplest case only. Let's imagine the simplest case. We have a game that contains two players, the max player and the min player. So without loss of generosity, okay, you have probably heard these phrases in mathematics a lot. Okay, max make the move first. It actually doesn't matter. They make the move first or me make the move first. It doesn't matter. Okay. Okay. At the end of the day, it's just the perspective differences. Okay. Okay. The game will actually can be defined as a search problem. Okay. And the search problem is that you have a bunch of states, and the state is the physical configuration of the chess pieces in the chessboard. And you also have operators that define the legal move. So you essentially can define a function that calculate all the available move that is available with the rulebook. Okay. Okay. So instead of well-defined, we are still putting the same paradigm as a single state problem. We are defining a function, and the function will take the current state and output the available actions and the next corresponding next state. The action is calculated with respect to the rulebook. Okay. Okay. So you need to make sure your move is conforming to the rulebook and do not make any illegal move. Otherwise, you will lose the game. And but one thing that is very, very different from the single state problem is that we will actually have a terminal test that determine whether we reach the end of the game, similar to the goal test. Okay. We need a function that determine whether we reach the end of the game yet. Okay. Finally, we have a utility function. The utility function is necessary because it tells us who win and who lose. Okay. Okay. When you are trying to simulate all the possible outcome of a game, you don't just want to know when the game ends. You want to know who win and who lose. Okay. If the max play, if the computer is simulating itself to be the max player, and it is trying to find a move that wins the game, then it will need to find a desired outcome that is the highest. If the computer is simulating itself to be the mean player, then the mean player would try to find an outcome that minimizes the outcome of the game. Okay. So any questions? Any questions? Any questions? Any questions? So essentially, we can if it is a two-person game like chess, okay, from the perspective of the max player, if the utility value is bigger than 0, then it wins. If the max player is if the outcome or if the final utility value is more than 0, then the max player lose. If the outcome is a draw, then the utility value is 0. Okay. You may think that okay, so I have +1, -1, and 0, then I can already represent the consequences of the game. This is actually the most simplest way you can represent the end condition of the game. But one thing I would like everyone to remember is that even you are winning or even you are losing, there is a difference between you win a lot and you win a little.
How much you win?
Yeah. So if you are designing AI, you want the AI to win the most. Right? You want the AI to win the most. If you are developing AI to beat human by design, you want the AI to choose a path that will make it win the most. Okay? Okay? So you want to find a route that makes the AI keep on winning. Okay, so this is one thing you need to know. You need to make into consideration. So +1, -1, and 0, although it works, but it is not a good way to represent the outcome of the game because you only know whether it's winning or losing or draw, but you don't know how big of a advantage that is. You want a numeric value that tell you how much you win. Okay. And this is this again we come across the search tree again. So here in this search tree, you are starting off with an initial state of the game. So this game is the tic-tac-toe. I don't need to explain what is tic-tac-toe, right? You don't need to explain what is tic-tac-toe, right? In Chinese, they call 井字過三關. Okay, I don't know what is it called in 普通話, but in English it's called tic-tac-toe. In Cantonese it's called 井字過三關. Okay, I don't know what is called in 普通話, so sorry about that. Okay. So in the tic-tac-toe game, I actually have a game board of three rows and 3 columns. Okay. Total, we have a square board of 9 cells. Okay. And max player will need to place the X, and min player will need to play the O. Okay. So it will need to both the max player will need to place 3x in 1 row, 1 diagonal, or 1 row, 1 column, or 1 diagonal. Okay. For min player, you need to find a way to put the O 1 row, 1 column, or 1 diagonal. Okay. So this is the game of tic-tac-toe. Okay. So now, how computer solve the game? I start off with a empty chessboard. Then among this chessboard, I have like 9 places that I can put the X, right? So I list out all of them and I declare all these nodes as the child node of the initial state. Then next round is the min player. Okay, so the min player would act on each state that is previously generated and try to generate its possible action. For example, if imagine now if the max player plays the X at this corner, okay, at the top left hand corner. So what is the chessboard that the min player observes is this one. Okay. And as a result, the min player would attempt to try out all its possible moves from this chessboard. And who can do the same for the rest as well. And after the min player make a move, then now we get back to the max player, and the max player will find a move on the chessboard now. Okay. Okay. So have you think about this? You can actually consider. Let's talk about this perspective. You can actually consider the search problem of finding the optimal path or finding the right action for the max player here is that I generate all the possible move, and among this move, I found the move that gives me the highest utility value. Right? So, but now, so let me repeat what I said. So looking at this diagram, okay, in order for the max player knows what steps should be taken in order to win in the initial state, it will need to calculate the utility score of all these 9 states are available. Okay, all these 9 states are the possible actions that the agent can make, and after making the action, the state generated. Okay. So after I generated these 9 states, I would calculate their utility value. And if I calculate their utility value, then the states that have the highest utility value will be winner. Will be the action that we want. And we select it, right?
But in the game of tic-tac-toe, there's no utility score, right? Because there's only
you can design a utility source. For example, I can count at the end state at the end state, how many white square I can have, okay? I will want to calculate, for example, if the end state have more white square, then I will believe that this is better because it ends the game faster.
More one. Oh yeah, because you use fewer moves.
Yeah.
Oh
Yeah.
Okay.
So let's get back to here, okay? So you can actually consider the problem of finding the best action for the max player at the top here as I generate nine possible actions, and among these 9 actions, I calculate the utility value, and I found the edge states that have the highest utility value, and I choose the corresponding action. If we consider it in this manner, then the problem becomes how we calculate the utility value of these 9 states. Okay? Okay. But this 9 state on its own is, we can consider this 9 state, each state on its own, a new initial state. The initial state for the mean player. Okay? Okay? So remember what we talked about in recursion. In recursion, we talk about one principle: divide and conquer. I repeat, divide and conquer. When you are taking the max player, the max player now has 9 moves, and I draw all the 9 moves available, and I need to find the utility score of this 9 moves. So you can actually consider this 9 state as a simpler problem than the original initial state. And to solve the initial state problem of finding the maximum best action available, you find the utility value for all these states. Okay, so when we repeat what I said, to calculate the utility value of the initial state, what you want to do is to calculate the utility value of the chosen 9 states, and you choose the state that gives you the highest utility value, and you pick the action. Then that's done. That is how you get the utility value for the initial state. Okay. Okay. So let's consider this. Okay. If the max player at the initial state want to know the best action, it wants to know the actions and also the final utility score for the initial state. So to do that, what you need to do is that you generate all the possible actions available and the new state available. For here, the chessboard here of the tic-tac-toe have 9 cells, so you can have 9 positioning available. So that is why you have 9 possible outcomes. And for these 9 possible outcomes, if I know the utility functions, if I know the utility value, then I can do the decision making. But now we actually convert the problem of calculating utility value of the initial state or into calculating the utility value of all these 9 chosen states. So we are actually breaking down a bigger problem into a small problem.
So it's like the uniform.
Similar. So you may find that, oh, Professor, why you spend so much time to talk about chapter 3? Because all the concepts you learn in chapter 3 is used right here at once again. Okay. Okay, so I will skip a lot of things, okay, in this lecture, in this set of lectures, okay. So in fact, you can consider the building of this search tree itself as a divide and conquer algorithm once again. In order for you to know the utility value of the initial state, you need to calculate the utility value of the chosen states. Once you calculate the utility value of the chosen state, then you know the utility value of the initial state. Similarly, if I want to know the utility value of these leftist nodes, okay, I need to calculate the utility value of all its chosen states. Then after taking the minimum, I can get the utility value for this state. Okay. For example, right now I want to find the utility value of this state. To find the utility value of this state, what I do is that I calculate the children looks utility value, and I take a minimum, then I can calculate the utility value of this state. Okay, so this is one pattern that we observe here. We are gradually dividing the problem into a similar problem for us to handle. Okay. Okay. If you do one more observation, if you take a look on what we are doing, we are dividing the tree into a similar structure. If we are dividing the tree into we are dividing the problem of finding utility value of a node in the search tree into a smaller problem. We keep on doing the problem division. We are dividing the problem of finding utility value into a smaller problem. We are doing divide and conquer work here. So tell me, how you are going to solve a divide and conquer problem? How you are going to solve a divide and conquer problem? Yes, recursion. So this is what we are actually trying to do in the minimax algorithm. But the recursion done here is done with two functions calling each other. Okay. So we have one function called the max value function that represents the max player, and we also have the mean value function that represents the mean player. Okay, and the max player will call the mean value function, and the mean value function will call the max value function. Okay, so the recursive call is done interleaving. Okay, in Chinese 梅花間竹式. Okay, so max player calling mean and mean player calling max, and keep this code keep on going. Okay. They are in fact the same similar function, but the majority differences is checking the doing the minimum versus the maximum choices. Okay, because max player need to maximize the gain, maximize the value, and the mean player need to minimize the value. So that is why then we have two functions, but fundamentally they are the same. Okay. Okay. So this is so-called the minimax algorithm. Okay. I understand that now we have a large language model called Minimax, but that Minimax is not the same as this Minimax, okay? Just to make sure everyone knows, okay? Nowadays, we actually have a large language model called Minimax, okay? But that Minimax is not the Minimax we are talking about in this lecture notes, okay? So it's two different facts, okay? I hope everyone understands this, okay? So what is called Minimax algorithm is that we are trying to simulate the whole cascade. Okay, the minimax algorithm is the exact algorithm. That builds the search tree. Okay, the minimax algorithm is the exact algorithm that builds the search tree. Okay, and the whole idea of the minimax algorithm is to break down the problem into a smaller problem. You initially want to find the utility value and the corresponding action for the initial state. But in order to calculate the utility value of the initial state, you need to know the utility value of the chosen state. And if you want to know the utility value of S1, S2, and S3, maybe I'll use the term, the number here, okay? So given the slides, okay, given the slides here, we have a search tree, right? This search tree is actually a very simplified version of the two-person game. In this game, you make a move, then your opponent make a response, then the game ends. Okay? Simple as this, I repeat. In this game, you make a move, your opponent make a response, then the game ends. Okay? This is the simplest situation you can have for a two-person game. Okay? And if you take a look here, now now I am trying to figure out the utility value of S0. To figure out the utility value of S0, I need to know the utility value of S1, S2, and S3. After I know the utility value of S1, S2, and S3, then I take the maximum value, then I know the utility value of S0. And subsequently, I also know the action that needs to be taken to lead me to the desirable utility value. Okay. But now then, how we are going to calculate the utility value of S1, S2, and S3. To calculate the utility value of S1, S2, and S3, for S1, you need to know T1, T2, and T3. And for T2, you need to know T4, T5, and T6. For T3, you need to know T7, T8, and T9. So there is one constant pattern right here, right now. You are actually dissecting the problem of finding the utility value to the child node. To know utility value of S1, you first need to know the utility value of S1, S2, and S3. To know the utility value of S1, you need to know the utility value of T1, T2, and T3. To know the utility value of S2, you need to know the utility value of T, T4, T5, and T6, okay? And so on and so on. So here, in this whole algorithm, we are actually keeping on dividing the bigger problem into a smaller problem. Okay, we divide it until it reaches the point we cannot further divide our problem. And here, the ending point is the terminal point. In the terminal point, the game ends, you cannot move further. The game cannot proceed further. So you cannot have another move. So you cannot divide the problem into smaller problem again, and you will stop right there. Okay, so T1, T2, and T3 are the terminal states. Once we reach the terminal state, we use the utility value to calculate its utility values for all the terminals. Then using the terminal's value, we can backtrace and calculate the utility value of S1 using T1, T2, and T3 utility value. Using T4, T5, and T6 utility value, I can trace back S2. Using T7, T8, and T9, I can trace back S3. Okay? And after S1, S2, and S3, I get the utility value. I can trace back S0. Okay?
S0 is S0 the maximum of
the maximum player's time. The maximum player's time. So S1 should take the maximum value of S1, S2, and S3. Okay? And S1 will try to take the minimum value between S1, S2, and S3. S2 will try to take the minimum utility value of T1, T4, T5, and T6, and so on. Okay? You should know this you must remember this rule, this concept. Okay, this is helpful to understand this algorithm. Okay, you may not really understand all the coding that I write here. Okay, but you must know how the minimax algorithm principally works. The game starts with the max player. And max player is having the initial state of S0. And max player can make a move of X, Y, and Z. So after making the X move, then it will be S1. Making the Y move, that will be S2, and making the Z move, that it will be the S3. Okay? Right? So after we if we have some ways to know the utility value of S1, S2, and S3, then by comparing the utility value of S1, S2, and S3, I know which one is the maximum, and I know the corresponding action. For example, just by in this graph, okay, we know that the S1 is 3, the S2 is 2, and the S3 is 3. The utility value of the S1 is 3. The utility value of the S2 is 2, and the utility value of the S3 is 2. So because S1 have a higher utility value, so S0 take its value, and from the perspective of the max player at S0, it know that after taking X move is the best for it, for it, okay? X move is the best move for the max player as S0. Okay? 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 So any questions? So if you are, so the next question is how we know the utility value of S1, S2, and S3. And for S1, okay, the mean player can make move as well. So the mean player, if he is at S1, then it can make A move, B move, and C move. So it can have the utility value, so it can have the terminal state as T1, T2, and T3. And T1 is having the utility value of 3, T2 is 12, T3 is 8. Because S1 is the minimum state player's turn. So minimum players will select the minimum value. And T1 is the minimum value, so S1 is 3. Okay? Okay. So for S2, because S2 is the mean player's turn, and S2, the mean player as S2 can make the move DEF, and DEF will lead to T4 to T6, these three terminal node. And the value and the utility value of these three terminal node is 2, 4, 6. So the S2 is taking 2 because S2 is the minimum player's turn, and it will take the action that minimize the utility value. So it will take the D move. So that is why the S2 is having the utility value of 2. And S3 is doing the same as well. Okay, so any questions? Any questions? Any questions? Any questions? So although it looks complicated, but it is doing things mechanically. Okay? You know the max turn, you know a turn is max player, then what it does is take all the child node, get the maximum value, and that's it, that is the utility value. If this is the turn of the mean player, you get all the utility value of the child node, taking the minimum value, then it becomes the utility value of that node. Okay? This is very mechanical actually, not as difficult as you believe to be. Although the coding here is very, very complicated, but you don't necessarily need to understand the full nature of all the coding right here. What you need to know is the principles. The principle here is that max player's turn will take all the child node, get its utility value, and choose the route that will make the utility value the smallest, the biggest. Okay. 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 And for the mean player, what if the turn is belong to the mean player? It will take the child node, take all the utility value of the child node, and select the minimum value. Okay. Okay. Utility value means the final outcome of the game at that node. Okay. Okay. So if the AI is actually taking an assumption, the AI assumes that both players are state-of-the-art players. Okay. So for the max player to consider is move. Max player to consider is move. What it does is it need to know the final outcome of all its child node, and it choose the outcome that will bring it the highest utility value, and that value will be the utility value of the state that is situated in. The same as the mean player. Okay. So that is why you will find that this algorithm is actually doing divide and conquer. It is dividing the problem of finding the utility value of a node as finding the utility value of the child node, and then you do an aggregation at the end, and that's it. Okay. So any questions? The actual coding, you don't need to understand the actual coding, okay? Very clearly. You can refer to it at your free time, but if I do not have the time, I will not go over it in great detail as well. Okay, but you must be at least sure how the utility value can be computed by your naked eye. You should be at least able to compute the utility value of the search tree of a game using your human mind. Okay, coding is another issue. If you know the principles, you are able to come up with your own implementation. But if you don't even know the logic, then it doesn't matter anymore. Okay, so any questions? Okay, and now it is 12:18. Okay, I probably would need to end. And before I end today's lecture, I will need to do some announcement because I see more students appearing right now. So I will want to do one announcement again. Okay, I've actually made this announcement at the beginning of the lectures. Okay, first of all, the group projects registration page is now available. Okay, you can register your group. You may think that, okay, this group registration page is very difficult to use, but don't worry, I actually provided PPT that explain how exactly is done. Just follow the procedure shown here and you are able to register your group. Please form a group of 2, or if you want to work on the project on your own, that's fine as well. On or before the 25th of March. That is the next week, Wednesday. Okay, and I will release the project specification and the tutorial detailedly discuss how the project should be done within this weekend. Okay, it depends on whether I have the time to discuss the tutorial. If I have the time, I'll probably discuss the tutorial at the end of the semester, at the end 1 or 2 lessons of the semester. And one thing I believe that most of you are very eager to know about the project presentation. Even if I need you to do presentation, I will do it in this style. I will ask you to record a video using Zoom and then send me a video, and that's it. Okay? 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 That is how simple it is. Okay? And another thing I would like to discuss is the examination. Okay? I believe that most of you are extremely concerned about one thing. That is whether the examination will contain programming questions. And I am going to very clearly tell you that although in past paper, we do have some fill in the blank question for programming question, but this year we simply don't have any programming question. That's it. Zero programming question for this year. Okay? Okay? Okay, you may take a look on the past paper. In the previous year, we do have one question that requires to do fill in the blank. But this year, we don't even have programming question in our exam. We just don't have programming question in our exam. So I hope I can make every one of you to feel a little bit relaxed. Because I believe that most of you are getting very afraid about doing programming during an exam in 2-hour time period. Okay, so one thing to make everyone comfortable and relax is that we do not have programming question in the exam. And if you want to know about how the exam is supposed to be, you can always check the past paper. It is always your right to check out the past paper. The past paper of almost all the courses in this school is available in the library system. Because I do not take my undergraduate here, so I don't know the exact step to get to the information. But I know that there is past paper available. Okay, maybe you can take a look on the library manual or something else. Okay, but as far as my memory is correct, you are always able to check out the past paper or almost all the courses in this university through the library. Okay, so it is your right to do so. Okay, but I will not provide any solution. Okay, so you need to figure it on your own. Okay, so this is the end of today's lecture. Okay, so I'll end the recording as well. Okay.